The topic for today is specific heat, and we kind of talked about this a little bit during lab yesterday. And you specifically experienced this through the balloon station. So, for example, you found out that when you blew up the air balloon, um, that one exploded quickly, as opposed to the one with water, which didn't even explode at all. So that has to do with specific heat. And so let's explore that topic. So let's say you're trying to make some ramen noodles, and you get two pots. You get a small one, you get a large one, and they're both going to boil at the same temperature. If you boil these two pots at the same temperature, is it going to take more energy to heat the large one, or less energy, or are they going to be the same energy? So we find out that when you have a larger pot with more water, it takes twice as much energy as it does the smaller pot. So the difference comes from knowing the differences between temperature and thermal energy. If you remember, temperature by itself is just the average kinetic energy. How much are you moving those molecules? And that's your temperature. As opposed to thermal energy, is a little more complicated. It's all the atoms, all the types of energies. For example, potential and kinetic energy. And this also depends on two things. One is mass and the other is temperature. So let's say you add heat to an object. How much will the temperature increase? Well, if I ask this question just the way it is, you won't really know. The answer is it depends. It depends on mass and material. How much mass do you have? For example, in the pot, we had either 1,000 or 2,000. And also the material. Are you using water or are you using something else? If you were to use oil, would that take longer, shorter? And these are the type of questions we ask with specific heat. So we see, for example, that it takes 4,184 joules to raise the temperature of water. Remember, joules is energy. So it takes a lot of energy to heat up water as opposed to 470 joules to heat up steel. This means that it takes steel less time to heat up than it does water. So specific heat in the book term is just how much heat is needed to raise the temperature. And this is all you really need to write in your notes up to this point. The rest might be needed for calculation purposes, but luckily we don't need to do that this year. So it's how much heat is needed to raise the temperature of 1 kilogram of material by 1 degree Celsius. And so you don't need to write the rest, but scientists use this part to calculate, to see differences between materials. But we can still do, we can still analyze graphs using this information. So let's say if you have a large specific heat, this means that you have to put a lot of energy into it. So the larger the number you see for that specific heat, more energy. Okay. If the specific heat is low, like steel that we were just talking about, then temperature will change relatively quickly because each degree change takes less energy. Right? So it takes less energy to increase the temperature of steel, as opposed to if the specific heat is high, like water, then the temperature will change relatively slow because it takes more energy. Okay, and the way I remember this for water, I just remember water has a high specific heat, and then you really want water to have a high specific heat because this means that, for example, if you're in the ocean and all of a sudden there's a temperature change, maybe 5-10 degrees, you don't want, water to feel so hot in the ocean that you can't swim anymore. Or let's say, for example, in Texas it's 100-degree weather. You don't want the ocean to all of a sudden take all that heat and become 100 degrees Celsius. That would mean the ocean would be boiling. So we're thankful that water has a high specific heat, because that means that it changes slowly and it takes more energy. So instead of doing calculations, we're going to analyze graphs, which makes it better, no math involved. So for example, let's say you have your graph on your notes, and we have temperature change on the x-axis, energy transfer on the y-axis. Well, if you see temperature change, we see that the red one, you put a line through it, changes the fastest. So let's say we have A. So temp change was quick. So if you look at your notes, you know that this has low specific heat. What does this mean? That means that if you heat this it'll heat fast, and it'll also cool fast, which is great. So metals are great for that. B, C, and D, their temperature changes slow. And this means that it's slow to heat, and that means that also they cool slower, so it takes a longer time to cool. So if I were to rate these, I'm gonna go up here. If I were to rate from low to high specific heat, I would say the lowest specific heat would be sample A, because temperature changes fast. Then would follow B, C, and D. So if I were to label these, I would probably say that the one that's fastest is some type of metal, like steel or something like that. And I would say probably the pink one, sample D, is probably something like water, because it's slow and takes a long time, takes a lot of energy. And that's how we would analyze our samples. To save you some time, I already color coded the substances that you'll be working with today: air, water, sand, and metal. And so you can use these colors to color code your graph. That means you don't need to plot your points. All you got to do is draw the graphs as shown here in the video. The only thing you need to look at is now to analyze what's going on. So for example, at the 60-minute mark, we notice that metal changed temperature really quickly. And if you remember from your notes, we know that it has a low specific heat. That means it changes temperature quickly, as opposed to water. It has a high specific heat. It needs more energy, so it's going to be slow. That's why we don't see a temperature change too high. Okay, so all you gotta do now is just put those on your graph, analyze the questions, get a stamp, and you're done for today.